Okay. Good morning, ladies and gentlemen. My name is Miss Komdao Termkleepbuppa. Today, I'm going to present my thesis in the topic of effect of simulated pulpal pressure on durability of microtensile bond strength of a universal adhesive. Here are the outlines. Let's start with the introduction. The universal adhesive is the most modern innovation of dental adhesive. It is designed to be used in multi-mode systems. Besides, it is also designed for both direct and indirect restoration. However, the compositions of the universal adhesive conduct them to perform more hydrophilic than other adhesives. Two limitations of hydrophilic adhesive systems are difficulty in elimination of water from adhesives and water attraction, which affect the quality of the bond and cause the incomplete penetration of resin into collagen fibers, leading to impaired bond strength value. The bond strength is amplified as the initial mechanical load to break the cross-sectional area of the bond. Nonetheless, the bond strength is used for giving the prognosis of the critical performance and longevity of the restoration. The objectives of this study were to evaluate the effect of simulated pulpal pressure on the durability of microtensile bond strength and investigate the micromorphological structure of the resin-dentine interface of dentine treated with single bond universal with and without simulated pulpal pressure. There were two null hypotheses in this study. The first is the microtensile bond strength of a universal adhesive bond to dentine was not affected by the simulation of pulpal pressure. Secondly, the microtensile bond strength of a universal adhesive bond to dentine was not affected by the thermocycling as an aging process. Next section. For the extracted style human mandibular third molar were used. A dentine disc with a remaining dentine thickness of approximately 1 mm was prepared by two parallel cutting, 2 mm above and below the CEJ using a slow-speed diamond saw under a water coolant. All pulpal tissue were removed and purified by 2.5% sodium hypochlorite solution, then soaking in distilled water. The 4D dentine discs were created a standard smear layer by wet polishing with a 600 grit silicon carbide paper, then rinsed with the distilled water for 5 seconds before the bonding process. The polished specimens were randomly divided into two major groups. S group for bonding process was done under the simulation pulpal pressure device with the sample size of 20. N group for bonding process was done without the simulated pulpal pressure device with the sample size of 20 as well. Then the bond specimens were in each group were further divided into two subgroups subjected to either the microtensile testing with an immediate testing group or testing after tensile thermocycling. A specimen in S group was fixed to a custom-made pulpal chamber, then connected for simulating pulpal pressure with an infusion pump that contained distilled water as shown on the slide, while the specimen in the N group was bonded independently without simulating pulpal pressure. Single bond universal was applied onto every specimen following the manufacturer's instruction. After light curing, the resin composite Filtech Z350XT was placed onto the bond surface. After kept in 37 degrees Celsius distilled water for 24 hours, our specimens were a longitudinal section in mesiodistal and macroconical directions to obtain slab-shaped specimens. The diameter of each bond interface of each specimen was gauged with a digital caliper to a size of approximately 1 mm square. 10 specimens from each group were subjected to the microtensile bond strength test after a 24-hour kept in distilled water. The remaining 10 specimens from each group were subjected to thermocycling for 10,000 cycles. For evaluation of microtensile bond strength, both non-aging and aging specimens were tested with a universal testing machine. For failure mode observation, each fracture specimen was identified the failure mode under a scanning electron microscope at 70 magnification. The failure mode was classified into 5 types. The first is adhesive failure at the dentine adhesive interface. The second is adhesive failure at the adhesive resin composite interface. The third is cohesive failure in the dentine. The fourth is cohesive failure in the resin composite, and the last is mixed failure. The nano-leakage was observed by silver staining at the resin dentine interface without argon ion beam etching. For the evaluation of the thickness of the hybrid layer, the specimen with argon ion beam etching were used for investigation. For statistical analysis of microtensile bond strength, our data show a normal distribution and homogeneity of variance. So two-way ANOVA and multiple comparison with Lankan were used for further analysis. The data of failure modes were statistically analyzed using the non-parametric Kruskal-Wallis test, and descriptive analysis was used for the interpretation of SEM images of the resin dentine interface. A statistical significance was considered at less than 0.05. The results of this study are studied from microtensile bond strength test. According to the graph, the simulated pulpal pressure device affected the microtensile bond strength value of both non-aging and aging group. For immediate testing group, the mean microtensile bond strength value of the NI group was significantly higher than the SI group, while the mean microtensile bond strength after 10,000 cycle thermocycling of the NT group was significantly higher than the ST group. The mean microtensile bond strength was also affected by 10,000 cycle thermocycling process. For the simulated pulpal pressure group, the mean immediate microtensile bond strength was significantly higher than the aging group. In accordance with the group with simulated pulpal pressure, without simulated pulpal pressure, the immediate microtensile bond strength was significantly higher than the aging group. For failure mode observation, our test specimen in SI and ST group demonstrated 100% adhesive failure at the adhesive resin composite interface. The dentine side of specimens was completely covered with the adhesive, and the dentinal tubules could not be detected. For NI group, expressed 100% adhesive failure at the dentine adhesive interface. The dentine side of the specimen was not covered with the adhesive, and the dentinal tubule were filled with the resin tags. The SEM images of resin dentine interfaces for our experimental conditions are shown on the slide. SI had the thickness of the hybrid layer approximately 1 micron with plenty of silver nitrate deposition along the bottom of the resin dentine interface. The ST had a 0.95 micron thickness of the hybrid layer with more silver nitrate deposition at the bottom of the hybrid layer than the SI. For the group without simulating pulpal pressure process, the thickness of the hybrid layer of the NI was approximately 0.98 micron with some silver nitrate deposition at the resin dentine interface. The NT had a 1 micron thickness of the hybrid layer with more silver nitrate deposition along the bottom of the hybrid layer than the NI. Now we'll continue with the discussion part. Single bond universal is defined as a universal adhesive with hema, which is considered to be a hydrophilic component. Existing of hema causes water retention in the adhesive layer, and it reduces water evaporation in the solvent, and also creates the water channel for pouring water from the dentine into the adhesive layer, which is prone to be degraded by hydrolysis. The result of immediate microtensile bond strength value obtained from simulated pulpal pressure group might be relatively lower than both simulated pulpal pressure groups and previous studies, which might be due to hydraulic pressure device. This machine is used for imitating the clinical situation for physiologically intrapulpal pressure simulation that push the dentinal fluid throughout the hybrid and adhesive layers, resulting in hydrolysis, endangering the long-term durability of the resin dentine interfaces. The negative effect of the simulated pulpal pressure on the resin dentine interface also affect the failure mode pattern. The simulated pulpal pressure might result in a change in pattern of failure from adhesive failure at the adhesive dentine interface of N group to adhesive failure at the adhesive resin composite interface of the S groups. Also, this condition of the aging process used in this study imitate in vivo physical aging of restorative materials by cyclic exposure to hot and cold temperature in a water bath that correspond to 1 year physical aging in the oral cavity. The stress that occur at the resin dentine interface associates with the different thermal contraction and expansion coefficients between the restorative material and tooth structure. It accelerates the hydrolysis of demineralized collagen and extracts poor polymerized resin oligomer by hot water, which endanger the bond strength. In the same direction with this study, both ST and NT group demonstrates statistically significant lower microtensile bond strength than the SI and NI, which were immediate testing group. Thus, an increase in silver deposition within the resin dentine interface in the group with thermocycling was observed. This confirmed the deleterious effect of the thermal aging on the degradation of the resin dentine interfaces. Therefore, all our hypotheses in this study were rejected. In conclusion, the microtensile bond strength value and nano-leakage of the resin dentine interface could be affected by simulated pulpal pressure and 10,000 cycle thermocycling process. To avoid endangering the bond strength, besides controlling the environmental moisture, clinicians should be pay attention on controlling the intrinsic moisture of the dentine surface as well. Finally, this thesis would not be accomplished without the mercifulness of Associate Professor Dr. Pison Senawong, a major advisor, and suggestion from Associate Professor Dr. Pipop Saikea, a highly co-advisor. Thank you.
Thank you for your presentation. Very nice. And this is time of Q&A. Welcome to you all and participant to ask her.
Thank you very much, Dr. Komdao, for your presentations. Is there any question from the audience? Ajahn Varasini, can you see? Is there anybody ask questions? No.
I cannot hear everybody. No question?
No questions. Okay, so Dr. Komdao, very impressive work, and I can see so many things and lots of things you have done through the projects. So I have just wondering before, because I did this before when it was in the graduate program, I also did the pulpal pressure as well. So I just want to ask your idea and share my idea with you. So in this case, which type of fluid you use in this study in terms of dentinal fluid?
Just distilled water.
Distilled water, right? So it's clear, right?
Yes.
It's clear, and I think I had that problem as well because it's hard to see the bubble inside the small tubing. So and my idea, what I did that I want to share with you is I got a recommendation from the expert, Dr. David Pashley. He recommended me to use the color dye, to add the color dye into the solutions. So it's much easier to see and observe the bubble inside the tubing. So maybe this can help you with your next or the future study. Okay. Okay.
Are there any effects of the dye?
That's very nice question because we're concerned about that as well. Dr. Pashley also remind me to beware of the pH when we add like a color dye. So we have to check the pH before we using it. That's a nice question. Thank you.
Thank you.
Okay, so if there is no questions, we have to move to the next topic. Thank you very much, Dr. Komdao.